Hey, physicists, want to go over a couple of the problems that seem to have caused the most issues on our most recent test from Topic2Cycle2 on accelerated motion. And I'll pick a little bit from each page. So on page 1, remember we ended up having objects that had forces applied to them. And we can see here that it says for each pair, circle A or B. For the object with the greater acceleration regardless of direction, circle equal, if equal. And B, describe the change of motion. That was a big issue. People talked about motion, they talked about forces, but it's looking for the change of motion, also known as acceleration of the object selected in A. Okay. So I take a look at first, these two objects, and I see they both have a net force to the left of 5 newtons. We've got 10 newtons to the left, 5 newtons to the right. This also has 10 newtons to the left, 5 newtons to the right, so I have a net force of 5 newtons. But remember that acceleration is equal to our net force divided by mass. These two objects have different masses. This is at 30 kilograms. This is 20 kilograms. So this will actually have the greater acceleration because it's lighter. Now describe the change of motion. Change of motion is the same as acceleration. So I can describe this as, let's see, box A will accelerate to the left. That's all that was needed. Few people actually calculated what that was, or if you ended up saying speeding up to the left or slowing down to the right, that would also be acceptable. Here, page 2, we had a student pulling a chair, weight of 20 newtons with a bungee cord, and collected the data before. So we have sequential measurements, bungee cord, we have 5 newtons to the right, and the velocity, you'll notice, is increasing from 1 meter per second to 3 to 5 meters per second. Okay, are the forces balanced or unbalanced? Well, if velocity is changing, that's the same as acceleration. If something's accelerating, I know the forces are unbalanced. And why is it unbalanced? Because the velocity is increasing. You can see that from 1 to 3 to 5 meters per second. In other words, I know that acceleration is equal to F net divided by m. If there is acceleration, there must be a net force. Let's go ahead and draw the qualitative force diagram. Take my chair, this will be for the chair, to reduce it to a single thought. I see that it is moving to the right, not up or down or anything. So I know that it has a weight of 20 newtons. So I have a gravitational force down, normal force up, and I'll have a tension force to the right. Notice our force diagram is unbalanced, same as here. Some people put friction. But if I did have friction, I better have friction so it was noticeably less than the tension force. I'd want to see that friction was less than tension. Scrolling to the bottom of the page, we had our one more follow-up question here. And there were a couple of different versions, but let me read this one. Phil thinks if he pushes the stroller with a net force, and the important part here is net force of 2 newtons, the stroller will safely remain at the same velocity. Is this theory correct? Why or why not? Well, I know that, is the theory correct? No. Okay, it's not correct. Why? Because if there's F net over m is equal to acceleration. If there is a net force, then there needs to be acceleration. Acceleration means that the velocity is changing. That's why it's not correct. It was really the same check as the question up here. Up here, you're giving that there was acceleration, and you need to recognize that there was a net force. Here, we're given a net force, and you're supposed to see that there is an acceleration. And maybe we wanted to add something because, okay, if there is acceleration, okay, then the stroller will change speed. And continue to change speed. It'll be going dangerously fast or something. Page 3 and 4 involved quantitatively solving problems, and let's go through those. I'll give an example where we're solving for acceleration, one for mass, and then one for force. Areas where students lost the most points on this one or seem to have a problem with were one, make sure they included units, and the other one was making sure they used the 5-step process here. So we have a crate dragged across an ice-covered lake, so we can think it's frictionless, or low friction. The box has a mass of 60 kilograms and is pulled by a net force of 40 newtons. We don't have to worry about how much friction there is. Maybe there's a force of 42 newtons and there's only 2 newtons of friction. There's a net force of 40 newtons. What is the acceleration of the box? Be sure to include units. Go through our 5-step problem-solving problem. First, picture. So we have our 60 kilogram box being pulled by a 40 newton net force. Next, what are we looking to find? That's right, acceleration. It's listed right there, acceleration of box. Okay. What are we given? We're given that the mass of the box is 60 kilograms and there's a net force of 40 newtons on it. Let's see what our relationships are. Well, we know we're trying to find acceleration, so let's find a relationship where acceleration is isolated. And acceleration is F net divided by m. That was also written on the board. Okay, let's go ahead and solve this using units. Okay, so our acceleration is 40 newtons divided by 60 kilograms. That gives us 0.66 newtons per kilogram. What's that mean? You'll remember that a newton is the same as a kilogram meter per second squared. So if we write that all out, our kilograms cancel. We're given 0.66 meters per second squared. Why did I go to 2 decimal places? Because our numbers were given to a precision of 2. So 0.66 meters per second squared. Okay, in this next problem, we have 3 people pushing a stalled cart, and each person pushes with a 400 Newton net force. What is the mass of the car if the car accelerates at 0.8 meters per second? Be sure to include units. Let's take a look. We got our picture. 3 people pushing a car, and we're trying to find mass. What are we given? Given our net force is 3 times 400 newtons is equal to 1200 newtons total. And let's see, our acceleration is 0.8 meters per second squared. Now, our relationship was an area that a lot of people had a problem with mass. I want to get mass all by itself, so let me go ahead and multiply each side by mass. I'm going to divide each side by acceleration just to get mass all by itself. Mass is equal to F net divided by A. My net force was 1200 newtons. My acceleration given over here is 0.8 meters per second. And we could see what our units were up here. When we cancel this all out and do the math, we get 1500 kilograms. Passes the smell test. Yeah, that's about right. It's not quite 2 tons. And our last problem, a tennis ball mass of 0.30 kilograms is accelerated at a rate of 150 meters per second squared when hit by a professional tennis player. What net force, that's what we're looking for, does the player's tennis racket exert on the ball? Be sure to include units. Here, our picture. What are we trying to find? Trying to find net force. What are we given? We're given mass, 0.30 kilograms, and acceleration of 150 meters per second squared. Our relationship on this one's our famous one, F net, is equal to mass times acceleration. No reason to do any complicated algebra there. Let's go ahead and solve this. So our net force is equal to our mass, 0.30 kilograms, times 150 meters per second squared, and we get 45 kilogram meters per second squared, and we normally call that newtons. So 45 newtons is our solution here. So if you're talking to yourself saying, oh, why didn't I do better? I think I do better again next time. Consider taking the retest.